Lesson 4. Role of satellites in meteorology and types of remote sensing technologies. First of all, on this page, we will start by introducing the topics in this module. These topics are: what is satellites? Why are satellites important? What do satellites do? Weather satellites. Role of satellites in meteorology. And types of remote sensing technologies. What is satellites? Dictionary definition: an artificial object placed in orbit around the Earth, Moon, or other planet for the purpose of gathering information or communicating. A communications satellite. There are two main types of satellites. These are natural satellites, e.g. Moon; artificial satellites, e.g. Sputnik 1. There are two types of satellites: natural satellites, artificial satellites. Natural satellites. A natural satellite is, in the most common usage, an astronomical body that orbits a planet, dwarf planet, or small solar system body. Artificial satellites. A satellite or artificial satellite is an object, typically a spacecraft, placed into orbit around a celestial body. They have a variety of uses, including communication, weather forecasting, navigation, GPS. Satellites fly above Earth, allowing them to see large areas and have a clear view of space. They are essential for modern life because they provide critical services in communication, navigation, and scientific research. Before satellites, TV signals couldn't travel far because they moved in straight lines and were blocked by obstacles. Communication satellites enable global connectivity by transmitting television signals, phone calls, and internet data across vast distances. What do satellites do? Satellites play a crucial role in communication, navigation, weather forecasting, scientific research, space exploration, and security. They enable global connectivity, provide GPS services, monitor environmental changes, and support national defense. From transmitting TV signals to studying distant galaxies, satellites are essential for modern technology and daily life. Weather satellites. The first meteorological satellite, TIROS, was launched on April 1, 1960, to demonstrate the benefits of observing Earth's cloud cover from space. Weather satellites are primarily used to track storm systems and cloud patterns, but they also detect environmental phenomena such as pollution, fires, auroras, dust storms, snow cover, and ocean currents. These satellites play a crucial role in weather forecasting, climate research, and monitoring environmental changes. Role of satellites in meteorology. Satellites have many uses in meteorology. We can say these as follows: 1. Weather observation and forecasting. 2. Storm monitoring and tracking. 3. Climate monitoring and change detection. 4. Disaster management and environmental monitoring. 5. Sea surface monitoring and oceanography. 6. Atmospheric composition and air quality. Weather observation and forecasting. Weather observation and forecasting are fundamental components of meteorology that rely heavily on satellite data for accuracy and precision. Satellite observations provide a global view of atmospheric conditions, helping meteorologists monitor weather patterns and predict future weather events. A weather observation. B. Weather forecasting. C. Types of satellites used in weather observation and forecasting. D. Impact of satellite data on forecasting accuracy. A weather observation. Weather observation involves monitoring the current state of the atmosphere, including temperature, humidity, pressure, wind patterns, and cloud formation. Satellites provide essential data by capturing images and gathering measurements of these variables from space. This data is then used to assess weather systems and track changes. Cloud monitoring. Satellites continuously track cloud formation, movement, and changes in cloud properties. Cloud patterns are critical indicators of weather, helping meteorologists detect storms, rainfall, and temperature changes. Temperature and humidity. Satellites equipped with specialized sensors, such as infrared radiometers, measure the Earth's surface and atmospheric temperatures. By observing temperature gradients, satellites help forecast weather changes, such as heat waves, cold fronts, or thunderstorms. Satellites also measure the moisture content in the atmosphere, crucial for predicting rainfall and cloud formation. Precipitation. Some satellites are designed to measure precipitation levels, including rainfall and snowfall. By detecting the intensity and movement of precipitation, meteorologists can predict short-term weather events like rainstorms, snowstorms, or showers. Wind patterns. Satellites help monitor wind patterns both at the Earth's surface and at higher altitudes. By tracking wind speed and direction, meteorologists can predict weather changes, such as the approach of a low-pressure system or the movement of a storm. B. Weather forecasting. Weather forecasting is the process of predicting future atmospheric conditions based on current observations and computer models. Satellite data is integrated into forecasting models, allowing meteorologists to make predictions about the weather for hours, days, or even weeks ahead. Here's how satellites contribute to the forecasting process. 1. Data assimilation into weather models. Satellites provide vast amounts of data on atmospheric conditions, which is then assimilated into numerical weather prediction (NWP) models. These models use mathematical equations to simulate the behavior of the atmosphere, allowing meteorologists to forecast future weather events. 2. Improving forecast accuracy. By observing the atmosphere in 3 dimensions, including temperature, pressure, and moisture at different altitudes, satellites help meteorologists predict a wide range of weather events such as thunderstorms, hurricanes, and cyclones. 3. Weather systems and fronts. Satellites help monitor the development and movement of weather systems, such as high-pressure and low-pressure areas, cold and warm fronts, and cyclonic activity. These systems are responsible for weather changes and are key to forecasting conditions like clear skies, rain, or snow. C. Types of satellites used in weather observation and forecasting. There are 2 main types of satellites used for weather observation and forecasting: geostationary satellites and polar orbiting satellites. Geostationary satellites. These satellites orbit at an altitude of around 35,786 kilometers, 22,236 miles, above the Earth's surface. They are positioned directly above the equator and move at the same speed as the Earth's rotation. As a result, they remain fixed over the same geographic area. Advantages: continuous real-time observations, ideal for tracking storms, cloud formations, and other fast-changing weather phenomena. Cloud imagery. Temperature and moisture data from the atmosphere. Monitoring of severe weather systems like hurricanes and thunderstorms. Polar orbiting satellites, LEO. These satellites orbit the Earth at a lower altitude, approximately 700 to 800 kilometers or 430 to 500 miles, and pass over the poles. As Earth rotates beneath them, they provide coverage of different regions at different times, capturing data on global weather patterns. Advantages: high-resolution data, useful for providing detailed observations of temperature, humidity, and other atmospheric conditions. Ideal for monitoring both local and global weather. Key features: high-resolution imaging of the Earth's surface and atmosphere. Detailed temperature, pressure, and humidity measurements. D. Impact of satellite data on forecasting accuracy. The integration of satellite data into weather prediction models has led to significant improvements in forecasting accuracy, especially in terms of short-term forecasting, severe weather warnings, long-term forecasting. Short-term forecasting. Satellites help provide accurate predictions of weather events in the next 1 to 3 days, including storms, temperature changes, and precipitation. Severe weather warnings. Satellites enable meteorologists to detect severe weather events, such as hurricanes, tornadoes, or heavy rainfall, early, improving response times and saving lives. Long-term forecasting. Satellite data on sea surface temperatures, ice cover, and atmospheric gases helps improve long-term climate and weather predictions, such as seasonal forecasts and predictions related to El Niño or La Niña. Storm monitoring and tracking. Storm monitoring and tracking is a critical application of meteorology that involves observing, analyzing, and predicting the behavior of storms to minimize their impact on life and property. Satellites play an indispensable role in this process by providing real-time data and imagery of atmospheric conditions. Here's a detailed explanation of how storm monitoring and tracking is carried out. Monitoring storm formation, storm classification, tracking storm movement, intensity monitoring, severe weather alerts and emergency planning, Technological advancements in storm monitoring. Climate monitoring and change detection. Climate monitoring and change detection involves the use of various technologies, particularly satellites, to observe, analyze, and understand Earth's climate system. It is crucial for identifying trends, measuring the impact of natural and human-induced changes, and predicting future climate scenarios. Conclusion. Climate monitoring and change detection using satellites provide an unparalleled view of Earth's systems, offering data critical for understanding and addressing climate change. By tracking changes in temperature, greenhouse gas concentrations, ice coverage, and vegetation, satellites enable scientists and policymakers to make informed decisions to mitigate and adapt to the ongoing challenges of a changing climate. Disaster management and environmental monitoring satellites play a critical role in disaster management and environmental monitoring by providing timely, accurate, and large-scale data essential for mitigating risks, responding to emergencies, and understanding long-term environmental changes. Conclusion. Satellites are indispensable for disaster management and environmental monitoring, enabling timely responses to crises and providing data critical for protecting the environment. As technology evolves, their role will expand, offering even more precise and actionable insights for a safer and more sustainable world. What is remote sensing? Dictionary definition. Remote sensing is the acquisition of information about an object or phenomenon without making physical contact with the object, in contrast to in situ or on-site observation. There are two main types of remote sensing. These are passive and active. Active remote sensing. A natural satellite is, in the most common usage, an astronomical body that orbits a planet, dwarf planet, or small solar system body, or sometimes another natural satellite. Passive remote sensing. A satellite or artificial satellite is an object, typically a spacecraft, placed into orbit around a celestial body. They have a variety of uses, including communication relay, weather forecasting, navigation, GPS. Active remote sensing. Active remote sensing refers to the use of sensors that emit their own energy, often in the form of electromagnetic waves, to illuminate the Earth's surface or objects, and then measure the energy that is reflected back to the sensor. Since the sensor actively emits energy, it can operate in any lighting conditions, including nighttime and cloudy weather. Key characteristics. Energy source. The sensor emits its own energy to illuminate the target. Data collection. The sensor measures the reflected or backscattered energy from the surface or objects. Advantages. Can collect data in the dark or during overcast conditions, as it does not rely on sunlight or external light sources. Examples of active remote sensing technologies. Radar, radio detection and ranging. Uses radio waves to detect objects, map terrain, and measure distances. Synthetic aperture radar, SAR, is a common radar technology used for high-resolution imaging. Sonar, sound navigation and ranging. Uses sound waves to map underwater surfaces or detect objects in the water. LiDAR, light detection and ranging. Uses laser pulses to measure distances and generate detailed 3D models of surfaces. Passive remote sensing. Passive remote sensing refers to the use of sensors that detect natural energy, usually reflected sunlight or emitted heat, that is already present in the environment. Passive sensors do not emit their own energy, but instead rely on the energy from the sun or natural radiation from the Earth's surface. Key characteristics. Energy source. The sensor detects naturally occurring energy, usually sunlight or emitted radiation from the Earth's surface. Data collection. The sensor measures the reflected or emitted energy from the Earth's surface or atmosphere. Limitations. Dependent on sunlight or ambient radiation, so it generally cannot operate at night or in cloudy weather. Examples of active remote sensing technologies. Multispectral imaging. Captures data in multiple wavelengths, such as visible light and infrared, allowing for the analysis of different materials and vegetation health. Thermal infrared imaging. Measures the thermal radiation emitted by objects, providing data about temperature differences on the Earth's surface. Photographic cameras. standard digital or film cameras that capture images using visible light.